Another important property that we need to build up in our algebra of matrices would be the zero matrix, the additive identity. For the addition of real numbers, the number 0 is the additive identity. That means if we add 0 to a real number, it will just give the real number itself. And a similar property holds for matrices. If A is an m by n matrix and 0, mn, is the m by n matrix consisting entirely of zeros, then A plus O sub mn is equal to A. So the matrix O sub mn is called the zero matrix, and it is the additive identity for all the set of m by n matrices. So for example, for a 2 by 2 matrix, our additive identity, our zero matrix would be 0, 0, 0, 0. For a 3 by 2 matrix, it would be 0, 0, 0, 0, 0, 0, and so on. So this is the additive identity or the zero matrix for all 2 by 2. This is the zero matrix for all 3 by 2 matrices, and so on. Now, when the size of the matrix is understood, the zero matrix may simply be denoted as O. Or if we need to identify, it should be O sub mn. In some books, they just use 0 then mn. But it's better to use letter O to determine that it is a matrix. Because remember, we denote matrix with capital letters. Now, zero matrices have the following properties. Given A is an m by n matrix and C is a scalar, then the following properties are true. Like what we have already defined a while ago, if we add A to O sub mn, therefore we will just have A because this is a zero matrix and the additive identity. Now, if we're going to add A to its negative, then it produces the zero matrix. So a specific example, if we will let A be equal to 1, 2, 3, 4, then that would mean that negative of A, which is negative of this matrix, would be equal to negative 1, negative 2, negative 3, and negative 4. Adding these two matrices, there you go, we will be having 1, 2, 3, 4, plus negative 1, negative 2, negative 3, and negative 4, which gives us 0, 0, 0, 0, which is our O sub 2, 2. Our O sub 2, 2, or our zero matrix for a 2 by 2 matrix. So there. Very similar to when we add A plus negative A, it results to 0 in the real numbers. Another similar property to the real numbers, if a scalar times a matrix is equal to the zero matrix, then it's either the scalar is 0 or the original matrix is a zero matrix in the first place. So, for example, given this A, then we were suddenly told that CA is equal to 0, 2, 2, because A is a 2 by 2 matrix, so I'm just going to leave it as O. That meant that if this is A, then C must be the scalar 0. Or, if we are told, I'm going to use a different example, let's say C is equal to 2, then CA is equal to the zero matrix, 0, 2, 2, then that would mean, let's just bring that down, then that would mean that if C is equal to 2, then A should have been equal to the zero matrix, to the 2 by 2 zero matrix rather, because we know that C is 2, but multiplying C to A made it O sub 2, 2. So that would mean that A is O sub 2, 2, or the 2 by 2 zero matrix. These properties of zero matrices made us able to further manipulate our matrices up to a point where we can solve a matrix equation. So just like this one. Solve for x in the equation 3x plus a is equal to b, where we are given with this one. So we are sure here that a and b are matrices, as given. So therefore, we're going to have x as another matrix. That's what we're going to solve. Now, this would mean that we have to apply the rules in the algebra of matrices that we've had so far, the properties of matrix addition, scalar multiplication, and the zero matrices. So, we're going to have this one here, 3x plus a equals b. Now, we cannot just simply use the shortcut transposition. We have to establish that one first. We know that because of the property of the zero matrix, A plus negative A equals the zero matrix, and this is 2 by 2. So take note that we are working with 2 by 2 matrices. I'm not going to encode it here anymore. So that would mean I can also add the negative matrix A here. And if I do that on the left side of the equation, I should do that to the right side of the equation as well. Now, this will now lead us to 3 times x plus the zero matrix is equal to b plus negative a. And we know that this will just be plus the zero matrix would just be 3x is equal to b plus negative a. Now, at this point, you might be wondering, sir, how come we can't just simply use transposition? Because remember, these are matrices and not real numbers. Transposition has been used as a shortcut for real numbers for a long time, but transposition with matrices is something that we have to be a little bit careful with. Although, for easy remembering, you can use it, but again, we have to be extra careful. So now here, at this point, usually we would divide by 3. However, we haven't defined any division with scalars. But we have defined rather scalar multiplication. That means I can multiply this by 1/3, and 1/3 times 3 is 1, which cancels it. And I can do the same for the right side. I should write it here on the other side. Wait a moment. So this should be 1/3. So there. There you go. So this is telling us that the matrix X can be solved by performing the operation 1/3 multiplied to b plus negative a. So we can do that. We can have the scalar 1/3 multiplied by our b. A moment. There you go. There we'll have our matrix B as here negative 3, 4, 2, 1 plus the negative of matrix A, which is 1, negative 2, 0, and 3. So performing this operation here, you can distribute 1/3 to both matrices, or you can add these matrices first. So therefore, I'll do that. I'll add the matrices first, and I'm going to have, this is negative 3 plus negative 1, that's negative 4, then 6, then 2, and negative 2. Finally, multiplying 1/3, I'm going to have negative 4/3, 2, 2/3, negative 2/3. So therefore, the value of our x is the matrix negative 4/3, 2, 2/3, and negative 2/3. And this is possible because of the properties of matrix addition, scalar multiplication, and of the zero matrices.